Hey everyone, welcome back to another video of mine, where today we're going to be solving Leetcode problem 72 titled Edit Distance. So we're given two strings, word 1 and word 2, and we have to return the minimum number of operations required to convert word 1 to word 2. We have the following three operations permitted on a word. Either we can insert a character, delete a character, or replace a character. So in example 1, we have word 1 and word 2 to be horse and Ross, respectively. And note that these are actually inputted as strings and not any other data structure. And we'd output 3 because that is the minimum number of operations required to do on word 1 to actually make it match word 2. So in the explanation, we can change horse to roars by replacing the initial H with an R. Then we can remove the R from roars, and this is going to be the R in the middle, not the first one. And then we can remove the E from rose once we actually end up by removing the R, and we'd end up with Ross, which is equal to word 2, which was initialized to Ross. And so since we have made three operations on word 1, which was initialized or set to be horse, we would output those total number of operations to be 3. And in example 2, we have an input word 1 and word 2 to be intention and execution, respectively. And we'd output 5 because in intention we'd actually remove the T and make it inention. Then in inention we would actually change it to be enention by replacing the I with an E. From inention we'd change it to exention by replacing the N with an X. From exention we'd change it to be execution by replacing the N with the C. And finally from execution we'd make it execution by inserting a U after that C. Okay? So I will give you guys a few seconds to kind of just go over this problem in your head and think of a valid solution, and then I'll tell you guys how I would optimally solve this problem in a few seconds. Okay, so for this solution structure, for the algorithm that we're going to be using, we're going to actually be using dynamic programming to solve this problem efficiently. And we'll do this by creating a 2D dynamic programming or DP table, where DP at I at index j, or basically the cell ij, will represent the minimum number of operations needed to convert the first I characters of the first word into the first j characters of the second word. And for the variables and data structures used, well, of course, we'll be using word 1 and word 2, which are these two strings that we want to convert between. We'll also be using a 2D list that we'll title DP, and this list will store the minimum number of operations at each step for substrings of word 1 and word 2. And finally, in this case, I'm personally going to be using M and N for my variables to represent the lengths of word 1 and word 2 respectively, just for easy access, instead of actually typing out length word 1 and length word 2 every single time we want to access those two variables. And yeah, so with that out of the way, let's just go ahead and dive straight into the problems, or into the solution rather. Okay, so like I talked about before, I'm going to initialize M and N to be the length of the word 1 and the length of the word 2. So again, we'll basically store the lengths of word 1 and word 2 into the variables M and N respectively, and this will actually help us iterate over these strings later on, as we easily can access these two variables M and N in a very quick time without actually having to type out length of word 1 and length of word 2 constantly. Once I actually do this, I want to actually initialize my DP2D table. So I'm going to set DP, basically that stands for dynamic programming, equal to nested lists of 0 times 0 times n plus 1, and using list comprehension I'll just use an underscore as my iterator placeholder for blank in the range of m plus 1. And essentially what this is doing is we'll basically create a 2D list DP that has dimensions of m plus 1 times n plus 1, or basically the length of words 1 and words 2, where each cell is initialized to 0. And the reason why we use m plus 1 and n plus 1 is to account for the case when one of the strings is actually empty. Okay, and now once we're actually done with that, we want to essentially have our fill in the base cases, right? So what I'm going to do is, underneath that, I'm going to say for I in the range of m plus 1, in that range, I'm essentially going to set dp at index I in this iterator at index 0 to actually be equal to index I. And basically in this loop, we'll basically initialize the first column of the dp table, where the value at dp at index I at index 0 represents the number of operations needed to convert the first I characters of word 1 to an empty string, which is simply just I deletions, right? Now we can actually fill in the second base case, which we basically say for, let's just say for j in the range of now n plus 1, or basically the length of the word 2. So for j in the range of n plus 1, I want to set dp at index 0 at index j to actually be equal to, you guessed it, j itself. And essentially what we do here is we will initialize the first row of the dynamic programming or dp table, where the value dp at index 0 index j represents the number of operations needed to convert an empty string to the first j characters of word 2, which is simply just j insertions. Now we actually have to populate this dp table. And so the way we'll do that is we'll say for I in the range of 1, starting from 1 till m plus 1, or basically m inclusive, or m plus 1 exclusive. And then for j in the range from 1 till n plus 1, or basically n inclusive or n plus 1 exclusive, we'll have a conditional to check if word at I minus 1, or index I minus 1. Okay, where's I? Okay, there it is. If at index I minus 1, if that's actually equal to word 2, sorry, I forgot word 1 here. If word 1 at I minus 1, if that's actually equal to word 2 at j minus 1, or indice j minus 1, then we have to actually set dp at I at cell value or index j to be equal to dp at I minus 1 and j minus 1. And of course, if this isn't the case and this conditional doesn't actually pass to be true, we'll have an else conditional here. And then if that's not true, if basically word 1 at I minus 1 is not equal to word 2 at j minus 1, then in that case we'll simply set dp at index I at index j to be equal to 1 plus the minimum value, okay, the minimum value of dp at I minus 1 at cell value j, the minimum value of that, and then the minimum value of dp at I at j minus 1, and after that also the minimum value of not only that, but also the minimum value of dp at index I minus 1 at index j minus 1. Okay, where's j? J minus 1, okay? And that's basically our else conditional. So to better explain this, this is basically the core of our dynamic programming solution, where we'll use two nested loops to fill in the dp table. And for each pair of characters, basically at word 1 index I minus 1 and word 2 index j minus 1, we will check if they are the same. And if they are, no new operations are needed, so dp at I, j is the same at dp at I minus 1, j minus 1. Otherwise, we will take the minimum number of the three possible operations, where dp at I minus 1 at j is for a deletion, dp at I j minus 1 is for an insertion, and dp at I minus 1 j minus 1 is for a substitution, and we will add 1 to account for the current operation, right? And once we actually do this, once we're actually done for every cell ij in this nested loop of the range of the lengths of word 1 and word 2 to fill out our dynamic programming table, now we can simply return, after we exit this nested loop, dp at m at n, or basically initially the lengths of word 1 and word 2. And unless I made any syntax errors here, this should be completely fine. This should be accepted. And to kind of just recap what line 18 does is we basically return dp at index m at index n, which contains the minimum number of operations needed to convert word 1 into word 2, right? So for an overall explanation of the code, this code basically uses dynamic programming or the dynamic programming algorithm to solve the problem of finding the minimum number of operations required from converting one word into another. It basically builds a 2D dynamic programming or DP table, where each entry represents the minimum number of operations needed to convert a substring of word 1 to a substring of word 2. We'll start by initializing the base cases where one of the strings is empty, and then we'll fill the DP table based on the minimum number of insertions, deletions, or substitutions required at each step. So for the time and space complexity here, the time complexity is going to be basically big O of m times n, where m is the length of word 1 and n is the length of word 2. And this is because we'll fill out an n by n table, and for each cell, we can perform constant time operations, worst case. And for the space complexity, this is also going to be big O of m times n, because we actually need to store the dynamic programming table, which has n plus 1 rows and n plus 1 columns, or the corresponding lengths of the word 1 and word 2 input strings. So that's basically it for today's video, and I hope this explanation was helpful, and if you enjoyed it, please consider liking this video and subscribing to my channel. It really does mean a lot. And without further ado, I will see you guys next time. Bye-bye.